So a steep mountain is inclined 74 degrees to the horizontal and rises to a height of 3,400 feet above the plane. Okay. And a cable car is to be installed running to the top of the mountain from a point 840 feet out in the plain from the base of the mountain. Okay. Keep track of those numbers. So it said, so we're going to have a base of the mountain. So let's draw the base of the mountain here. And the angle that it rises is 74 degrees. 74 degree mountain. So 74 degree mountain. And this mountain climbs to an altitude of 3,400 feet. So if we, so if we go, well, my drawing's a little wacky today. This height right here of the mountain, up to the tip of the mountain, is 3,400 feet. Now, where it gets a little tricky to understand is they said that from the base of the mountain, you moved away 840 feet. So from here, you move 840 feet. And then the tram line runs from here to here. We have the height of the mountain, which means you can find this edge. We don't know this angle. It says find the shortest length of cable needed. So that means, so we need to find this edge right here. There's two ways to go about this. One of them is to just use right triangle trig, because you can find this distance, you can find this distance, then you'd know this distance. The only thing is you don't know this angle, and you have to do a lot of work to get there. So you'd have to use tangent then to, once you find this, there's just a lot of steps to get there. Law of cosines, exactly. So this angle right here, we can do 180. So 180 minus 74 would be that angle right there. And so that's 106. And so once you have that angle, now I know that this is 840. So if I drew a separate triangle now off to the side of just the piece that I'm looking at this triangle that, oh my Lord, let's try that again. For some reason, some days my panel is slicker than others, and I don't know why that is. Yeah. Okay. So that's why I bought a new one. I just haven't set up the new one yet. Okay, so that's 106. This is 840. Once you find this edge, then you can use the law of cosines. So let's go ahead and find this edge then, if it's still looking familiar. So I have, this would be opposite side of this triangle right here. So if I look at this inner triangle, this right triangle. Yeah, I think this pad is dying on me. That's why I bought a new one. So we could write, that would be opposite and hypotenuse. So that would be the sine of 74 is equal to 3,400 over that hypotenuse there, which I don't want to call H, I'll call it C or something. So that means C is equal to 3,400 divided by the sine of 74. So once you get this C value, then you're going to have this. Okay. And let me just real quickly, I do want you guys to see at least once how to set up law of cosine. So this is a good example for that. So 35, 37.02 about. Now I have enough information to do law of cosines, because now in this I have this piece, which is my side. That should not be degrees, that's feet. Don't ask me why I put that. There's my angle. And this is another side. So this is side, angle, side, which is definitely law of cosines from our discussion yesterday. And so whenever you have two sides and an angle, you're going to, or more sides than angles, you're going to use law of cosines with the exception of the ambiguous case, which is what I'm going to talk about here in a minute. If I fill this out, it doesn't matter how you label these as long as you're consistent. So if I call this C, then this would be angle C. If I call this A, this would be angle A. And if that means that this would be angle B in little case b. And so the angle that I have is B, which means I would start with the version of the law of cosines that has B squared. Okay, because I want the version that has cosine of B at the end. So then it would be B squared equals A squared plus C squared minus 2AC cosine of B. That would be the version of the law of cosines I would use based on the way I labeled this triangle. And it's all about where's your angle. So this angle is angle B, so that needs to be a lowercase b out here. Okay, and then you fill in your information. So we don't know the length of B, that's what we're trying to find. We do know A. We do know C. We do know A and C again. And then we do know angle B. And the big thing here is that if you have a calculator that doesn't follow the order of operations properly, you're going to have to really be careful about how you calculate this. So like if you have an old scientific calculator, you'd have to calculate this piece first, put it in your memory, calculate this piece, and then subtract the two. Okay, but most graphing calculators, you can just enter in the expression. It will follow the order of operations properly. The law of sines ambiguous case is the one case when you have two or you have more sides than angles, but you don't use law of cosines. In order to do it though, you have to understand that there are problems with it. And so I'm going to go to my open math and share my screen, section 10.1. And I added a link down here for the ambiguous case because it lets us see why there's a problem here. Okay. So depending on the information you're given, if you're given an angle and two sides, it's actually possible that no triangle exists. So like in this case, if I had a side length of 9 and another side length of 3, notice that it can't even form a triangle. Okay. If I make the angle bigger than, oh, I can't see that now. There we go. So if I make the angle bigger, notice that that doesn't, even though there's a triangle over here, this angle is no longer inside the triangle, so this doesn't even apply. Okay. So there's, if I'm out here, there's only one way I can actually form a triangle, and that's for A to be longer. And notice, there we go. So once A is longer than B, then I get an actual triangle containing that angle. Okay. But if I'm less than that, then the angle is no longer in the triangle. It's all screwed up. Okay. So that's, so if the angle is bigger than 90, then this side has to be longer than the other one. Okay. All right. But the ambiguous case, there's only one triangle here that works. The ambiguous case is specifically when the angle is smaller than 90. And let me move this back over. And then, there, how's that? Well, it's swinging for a reason, and I'll explain why. I'm going to explain why it's swinging. So notice that it's swinging because it's trying to connect up to the baseline of the triangle here. Okay, right now it can't connect because A is too small. Once A gets to be just the right length, and unfortunately I can't get it exactly the right length. Let me put a nice measurement in here. There we go. Okay, so if I get this exactly the right length, what kind of triangle do I make? It's a right triangle. There's only one solution, but that's only if these two are related by the sine of this angle directly. Once A gets longer than that, notice that this length can swing to two different positions and actually form a triangle. There's actually two triangles here that are possible. This one and the bigger one. Because this side length, this A side length, could swing over to here, or it could swing over to here. That's why it's swinging back and forth. Okay, that's called the ambiguous case, where this edge can swing back and forth. And there's a specific case where that happens. So SSA is the ambiguous case. And the time when you have two solutions is if the angle that you're given is between 0 and 90. Okay, so if you have an acute angle that you're given, and the opposite side is greater than B sine of A, because if it was actually equal to B sine of A, you'd get a right triangle. So if it's greater than that, okay, but less than the length of the other side. So this is the ambiguous case. If you've got an acute triangle, so an acute triangle, acute angle that you're given, and the side opposite that angle, so the opposite opposing side, is trapped between these two values. That's the ambiguous case. So as an example, let's suppose that I said to solve the triangle where angle A is 35 degrees, side A is 15 centimeters, and side B is 20 centimeters. And so I can check to see if this is the ambiguous case by first figuring out what B sine of A is. Now, if the triangle has been labeled differently, so like if I rearranged all these letters, you couldn't just magically use this formula anymore. This has to be the adjacent side here. So whatever the labels are, don't just use A, B, and C. You have to make sure you understand what's going on. This is the adjacent side to the angle. That's really important. Okay. And so if the triangle's been labeled differently, you'll have to make a mental shift there or relabel the triangle. You can always relabel it. But in this case, I gave you the labels correctly because it's the first time you've seen it. So if I drew this, I'd have a 35-degree angle. I have the adjacent side, so this is angle A. The adjacent side, because the opposing side would be over here. That would be A. That means this side has to be the adjacent one. So, and you could also do down here, but we usually leave this as the baseline of the triangle. So that's why I put it up here. So 20 centimeters. And if I calculate out the adjacent side times the sine of the angle, so 20 times the sine of 35, I get, so 35 sine of that times 20. And I get 11.4715. about. Is this bigger than this? Yes, so this side that we're given over here is longer than this. The reason I do this calculation is because this length right here is actually the height of this triangle. This is called h. So h, the height of the triangle, because that would force us to be a right triangle then, and then I could just use right triangle trigonometry. This is h, the height or altitude of that triangle. And as long as we're longer than that, then I know it can connect up. If we were exactly equal to that, it would make a right triangle. But I also need to make sure that the side is not so big that it can't fold in on itself. If it's a really big side, I can only go this way, which means there's only one solution. But if it can swing back and forth like the interactive, then there's two solutions. So I need to know, is this length less than this one? Because if it is, then it can swing backwards and forwards. And so I would look at that and I say, okay, in this case, 15 is definitely less than 20. Okay, so what I've just found out is 11.4715 is less than 15, and that is less than 20, which is the relationship up here. So if the opposing side is trapped between this and this, so the height of the triangle and the adjacent side, then that's the ambiguous case. That means there are two possible solutions. Okay, that's why it's called the ambiguous case. There's more than one solution. Now that we know that we are in this specific case where the opposing side is longer than the height of the triangle and shorter than this side, the adjacent side, there has to be two possible solutions. So I'm going to draw a baseline here and a baseline here. We've got a 35-degree angle and a 35-degree angle. That's supposed to be a 3. And we've got a 20-centimeter side and a 20-centimeter side, and then we've got a 15-centimeter side, and there are two ways to draw that. One is to extend this edge out and draw the 15 centimeters going this way. And the other is to fold it backwards this way. Those are the two triangles that can be drawn meeting our criteria. So I've got two different possibilities, and that's what makes this problem challenging. However, there is symmetry here, because if I remember that line that I drew down, so if I take the height of the triangle, just draw it straight down, turns out that there's a triangle here that is symmetric. So this triangle, oops, and this triangle are the same triangle. They're just flipped different directions. One is flipped to the right, one's flipped to the left. So that's actually how you break this problem open is you use that symmetry to help you figure out what the two possibilities are. You'll start by finding one of the possibilities, and then you'll use that information to find the other. This one is the one that's usually easier to solve. And so if we start with this one, I'd use the law of sines, because if I'm going to just label this. So this is angle A, this is side A, side B. And so I need to figure out what one of the angles is. I'm going to go for this one because I already have this side. So then using the law of sines, A over the sine of A has to be B over the sine of B. And then I can fill in the information I know. Let's see, 20. But I don't know this angle yet. Okay. And the reason I want to start with this one is because in this triangle, what kind of an angle is B? It's acute. There you go. And inverse sine will give you acute angles back. But in this triangle, if I look at the angle B, because remember this over here, angle B becomes obtuse. Okay, and you won't get that one directly. That's why people who encounter this case very rarely get both solutions, and they think there's only one possibility. Then we can solve for angle B. So if I do cross multiply and divide, that'd be 20 sine of 35 over 15 is the sine of B. And then if I take inverse sine of both sides, then I can find out what one of the possibilities is for angle B. And so if I go to my handy dandy calculator, and you guys can double check my work here, I got approximately 49.89 degrees. Now, the thing that's cool about this is to continue solving the triangle, I now have enough information to go in and find all the other sides because I have two angles, which means I can go find the third angle. Once I have the third angle, I can go use either the law of cosines or the law of sines to find the other side. So I'm almost done solving this example. The problem is how do I make the leap from here over to here? And the trick is to look at this part of the drawing. So then if I look at this part of the drawing, so this baseline and this piece right here, this triangle right here is the same as this triangle just flipped around, which means that this angle, 49.89 degrees, is this angle right here. So then what does this angle have to be? 180 minus that. And so then that means that this angle inside this triangle, inside this really weird looking triangle, which looks kind of like, well, not quite like that, but kind of like that. I know that this is 35 degrees because that was originally given. Now I can calculate this angle, which is, let's see, that'd be 131.11. And now that I have these two angles, then I can go find the third angle by using the fact that angles add up to 180. Same thing up here. I can, once I know that this angle here, then I can look at the whole triangle. I know that this is 35 now. I know that this is 49.89. I can go find this by adding these together and subtracting from 180. And I already know this side, and then there's only one remaining side left, and I can use either the law of cosines or the law of sines to find that.